Welcome to Chem Help ASAP. This video is a review of many acids that students see during a 2-semester sequence of Organic Chemistry 1 and Organic Chemistry 2. You can't talk about acids without mentioning bases, so we will mention a few bases in this video as well. The list of acids covered in this video is not complete, but it should provide a somewhat thorough coverage of what most students will encounter and remember in organic classes. Your instructor may focus on a few different acids. If I left out something obvious, let me know in the comments section and maybe I will make a follow-up video. Finally, this video is intended to be a review and is recommended for students who have already learned some organic chemistry as opposed to beginners to the subject. Acids are for protonations. They add a proton to a molecule. If you encounter a reaction that is under acidic conditions, then your first inclination should be to protonate something. That is a pro tip. This video focuses on Bronsted acids, that is, acids that donate a proton, H+. Lewis acids, which are electron acceptors, are also important in organic chemistry, but they are more prevalent as you get into higher levels, not intro-organic chemistry. What do acids do in reactions? We know they protonate things, but we can be more specific than that. I tend to think of acids as doing two things. One, they initiate reactions through protonation. So the first step is a protonation. This normally happens with strong acids. Strong acids are strong because they are highly reactive, unstable. By adding a proton to another reagent, the acid transfers its reactivity and instability to the other reagent. That step, that transfer, is the event that starts the chemical reaction. The second thing that acids often do is protonate an unstable, electron-rich intermediate at the end of a reaction. This is a reaction quench and normally involves weaker acids. The reaction is over, but there is still some reactive anion floating around. The weak acid protonates this intermediate and puts an end to the reaction process. Okay, that's enough background. Let's work through some acids. We'll start with the strong acids and move our way to the weaker ones. Here are the strongest acids. They all have a pKa of 0 or less. For this slide, we are emphasizing sulfuric acid, phosphoric acid, and a lesser used acid, tosic acid, or para-toluene sulfonic acid. These are very strong acids. They are excellent for tasks like protonating an alkene to make a carbocation, protonating an alcohol to make a leaving group, or protonating a carbonyl to make a stronger electrophile. What is excellent about these particular acids is that their conjugate bases, the A- counterions, tend to be very poorly nucleophilic. So the conjugate base forms and does not try to get involved in the reaction so that something else can do the chemistry. Attack the carbocation, kick out the leaving group, or attack the electrophile. While I list 3 strong acids on this slide, sulfuric acid is by far the most important acid on this slide. If you need an acid to protonate and not do anything else, then sulfuric acid will take care of you. Here are some more strong acids. These also have a pKa of 0 or lower. They include the strong halogen acids, HCl, HBr, and HI, but not HF, along with hydronium, H3O+. These strong acids do the same tasks as sulfuric acid from the previous slide. They make carbocations, leaving groups, and strong electrophiles. What is different is all these acids form nucleophilic conjugate bases that can react with these intermediates. The halides, chloride, bromide, and iodide have varying degrees of nucleophilicity. Even water, the conjugate base of hydronium, can be a nucleophile for carbocations and protonated carbonyls. That's fine as long as you want the conjugate base to react with your intermediates. Note that I am excluding HF on this page because HF, despite the high electronegativity of fluorine, is not a strong acid. HF is very rarely used in organic chemistry. Notice that the reaction intermediates that are formed can also serve as acids. Carbocations can be deprotonated, loss of a beta hydrogen to make an alkene. That is an E1 reaction. Protonated alcohols can be deprotonated. This same goes with protonated carbonyls. So keep in mind that these intermediates are acidic, strongly acidic. Let's move to some somewhat weaker acids. On the left we have acetic acid, abbreviated ACOH. Here is the structure of acetic acid or ethanoic acid with an acetyl group, AC, and an OH. Acetic acid is a very useful acid, but it's not commonly listed as an acid reagent in reactions. One example is the use of acetic acid in the alpha halogenation of ketones. The role of acetic acid is as an acid catalyst to facilitate formation of the enol tautomer, which is what gets halogenated. The other weak acid is ammonium chloride, which is normally used in concentrated aqueous solutions. I do not normally mention ammonium chloride in my courses, but I know that some people do. Sometimes people will use ammonium chloride as a very weak acid to neutralize basic reactions. This is a reaction quench. Here we have water and alcohols. You might say, hey, aren't these just more weak acids like what we saw on the previous slide? Well, yes they are, but while water and alcohols are weak acids, many consider these to be non-acidic as they do not lower the pH when mixed with water. So these are very weak acids. When these are specifically used as acids in organic chemistry, they are normally quenching strong bases to stop a reaction. An example is on this slide. In a lithium aluminum hydride reduction, the reaction forms an alkoxide, a tetrahedral intermediate in the reaction after hydride attacks the carbonyl. This tetrahedral intermediate will remain in solution until it is protonated through the addition of water. That protonation forms the final product, the alcohol. Okay, this slide is the end of the reagents that most people would recognize as reagents that you use for their acidic behavior. The remaining 3 slides are a bit more obscure and definitely less acidic. Our first additional acid is the alpha hydrogen of carbonyl compounds. The pKa of alpha hydrogens is around 20. For ketones, esters are closer to 25. These are very weakly acidic. When deprotonated, carbonyls can form enolates, which are super useful in a range of organic reactions. Deprotonation of alpha hydrogens requires strong bases. Here in the middle is our ketone. Sodium hydroxide is a strong base, but it is barely able to deprotonate a carbonyl at the alpha carbon. NaOH achieves less than 1% enolate formation, but sometimes less than 1% is all you need to get a reaction started. LDA is a much stronger base. It achieves essentially 100% deprotonation with complete enolate formation. Our second additional acid is the hydrogen on the end of a terminal alkyne. This is an even weaker acid with a pKa of about 25. These hydrogens, when removed, form acetylides, which are a very useful nucleophile in organic chemistry, like carbonyl compounds, nobody would go into lab and ask for a bottle of alkyne to serve as an acid. Regardless, we can deprotonate terminal alkynes. Our base for this specific deprotonation is NaNH2, sodium amide, and here is our acetylide product. A fair question is, why not use NaNH2 to deprotonate carbonyls and make enolates? Sodium amide is a strong enough base to make enolates, but the NH2 anion is also a strong nucleophile. It would attack a carbonyl instead of deprotonating it. We can use NaNH2 as a base for alkynes because alkynes are not electrophilic like a carbonyl. There is no competing nucleophile-electrophile reaction with alkynes. Finally, our last additional acid is ammonia. This seems crazy. As you likely remember from general chemistry, ammonia is a base, not an acid. Well, if the base is strong enough, ammonia can also be an acid. Its pKa is very high, about 35. This is a very, very weak acid. It does serve as an acid in a dissolving metal reduction. These are reductions of alkynes to give alkenes. The hydrogens that are added to the alkyne arise through protonation reactions, protonations in which ammonia serves as the acid. So in this reaction, lithium dumps electrons into the alkyne and makes a radical anion. This is a carbanion, a super strong base. The carbanion deprotonates ammonia to neutralize the anion. The resulting radical picks up another electron from lithium. That makes a new basic carbanion, which is again protonated by ammonia. So while we don't think about ammonia as an acid, if the base is strong enough, then ammonia can definitely serve as an acid. That was a quick review of acids, some common, others not quite so common, in Organic 1 and Organic 2. Thank you for watching until the end. Please leave a comment, leave a like, or subscribe to the channel. Take care.